It's 1963, and the Cold War is raging. The Soviets and Americans bristle with nuclear weapons. Nuclear war is a constant and very real threat. Testing of nuclear weapons is common, in spite of the dangers of radioactive fallout. In October, the USSR and USA signed the Partial Nuclear Test Ban Treaty. The treaty bans all nuclear testing in the atmosphere, underwater and in space, but it allows limited testing underground. 3 days after the treaty is signed, the United States Air Force launches a pair of satellites. The satellites are codenamed Vela, which is Spanish for Watchman. Vela satellites are spy satellites designed to spy on the Soviets and make sure they don't break the Nuclear Test Ban Treaty. Although launched in pairs, the satellites operate on opposite sides of the Earth. All areas are under direct surveillance at all times. On board Vela are special instruments capable of detecting a nuclear test. Nuclear explosions emit different types of radiation across the electromagnetic spectrum. Vela carries X-ray detectors that pick up the flash of a nuclear bomb, gamma-ray detectors that record traces of a nuclear event, and neutron detectors to register the detonation. The Soviets can't hide from Vela. Vela can detect a nuclear blast even if it occurs on the far side of the moon. It's 1969, and scientists at Los Alamos National Laboratory are examining the data collected by Vela 4. This is painstaking work done entirely by hand, comparing column after column of numbers for differences. Scientist Ray Kleber-Sattel makes a major discovery, uncovering a sudden burst of gamma-ray activity. Did the Soviets detonate a nuclear weapon in space? Kleber-Sattel and his colleagues work out that the gamma-ray radiation they are looking at isn't the sort normally associated with a nuclear bomb. Because the radiation occurs in space, this is clearly an astronomical event. Astronomers know things like supernova and solar flares generate gamma-ray radiation. But the data recorded by Vela 4 doesn't match with any of these events. Scientists can't explain the first recorded gamma-ray burst. It's 1973, and the gamma-ray bursts documented by the Los Alamos team are declassified. Astronomers take up the investigation, but they don't have the technology needed to study where gamma-ray bursts come from. Are they from deep space? Or our own galaxy? Gamma-ray bursts are difficult to study. They are transient events, often lasting less than a second and appearing randomly across the sky. By the time astronomers focus their telescopes in the right direction, the gamma-ray burst is no longer visible. It's a lot like trying to locate a lightning strike after it happens. Over the next 20 years, many different theories appear. Some newspapers even report that gamma-ray bursts are nuclear wars between alien races. And because scientists don't actually know what they are, these reports can't be disproved. It's 1991, and astronomers get closer to the truth about gamma-ray bursts with the launch of the Compton Space Observatory. Instruments on board not only record thousands of gamma-ray bursts, but also map their distribution across the sky. If gamma-ray bursts were happening in our galaxy, the map would show them clustered along the Milky Way. Instead, the map shows gamma-ray bursts spread equally across the sky. So where are gamma-ray bursts coming from? They're actually outside of our galaxy, billions of light years away. It's 1997, and a new satellite, equipped with more precise instruments, makes the breakthrough astronomers have been chasing for decades. The BAPO-SAX satellite allows astronomers to finally pinpoint the location of gamma-ray bursts in the sky. But what is a gamma-ray burst? Because they come from such vast cosmological distances, astronomers realize gamma-ray bursts are events of incredible energy. But what sort of cosmic event releases this much energy? Astronomers begin the search to find out. The 21st century belongs to sophisticated satellites such as SWIFT. SWIFT carries advanced equipment capable of imaging the source of gamma-ray bursts in different wavelengths. It is linked to an enhanced communication system. SWIFT can send accurate coordinates of gamma-ray bursts to ground-based telescopes in less than a minute. This means astronomers can study the after effects of a gamma-ray burst, the afterglow. Astronomers now know there are different types of gamma-ray bursts, and that some of them are linked to events like supernova. It might have taken over 40 years, but astronomers are closing in on the truth about gamma-ray bursts.